want to go back a little bit. I want to give a reformulation that's not in, oh, here's Mario. Back, okay. I want to go back and give the definition of the topological entropy as a kind of warm up for the version that I want to give. So there's two versions. There's two standard versions. I actually want to give the more metric of the versions because it's a little less fiddly with like talking about open covers and so forth, but it's sort of easily equivalent to the open set version. So again, we're in the same setting. We have a compact set, and I said this is going to be the more metric version, but now we're going to take any metric, but then it won't depend on the metric. And you define derived metrics. Let's define a derived metric depending on the dynamics, and the kth derived metric will be you ask for 2 points to be close here, you ask that they be close for k steps. So that f of x and y have to be close, f of x and f of y have to be close, and you keep going up to the kth step. Sorry, no, don't desert parentheses there. The kth iterates all have to be close. And the various variants, this is the one, I mean, we're doing a dynamics which is not invertible, so I can only iterate forward. And then the entropy is about a, it's not usually phrased this way, but I want to think about it as a kind of volume, kind of the epsilon volume of a space with respect to some metric. I'll apply it to these dk metrics in a moment, but this will be the minimal size of an epsilon net. So some set of points x1 through x capital N, so that the union of the balls around the x sub I of radius epsilon, so that they cover the whole space. By compactness, this is some finite number, and I'm just asking for the minimal such thing, which of course isn't necessarily easy to compute. But I'm about to take a limit, so you only need to approximate it. So the topological entropy is the limit as epsilon goes to 0 of the limit. If I fix epsilon, I can take the limit as n goes to infinity, and I can take this volume with respect to these derived metrics. To be close here gets more and more stringent. These metrics get finer and finer, so I expect more and more balls. I expect it to grow exponentially, and I am missing a log in here. And I look at the rate of exponential growth, and that's the topological entropy. Great. So that's the topological entropy. Now I want to do a thing for following the same sort of principle. I want to think about distances rather than volumes. So again, so I have some metric space, and before I introduce dynamics, let's introduce a kind of distance. This is a little lowercase x. So the distance between 2 points, little x and y inside big X, this is going to be the minimal instead of the minimal things covering the whole space, it's the minimal length of an epsilon chain connecting X and Y. So that you have some set of points x0, which is x, x1, and so forth, to some x capital N, which is equal to y, and so that the distance from xi to xi plus 1 is less than epsilon. I wrote it as a distance. This is, of course, not a metric. It doesn't really matter for what I'm about to do. Maybe you could correct it to make it an actual metric, but I want to just stick with this definition. And for this to be interesting, I want this to be at least locally path connected, so that I can find such chains for at least some pairs of points. Great. This is a fairly standard definition, but what's going on with this expansivity? Now let's go back to the case where we have some dynamics here. And now I'm going to work with any metric. And again, I could rewrite this in terms of open covers if I wanted, but I want to define, this is a term I came up with today, but the distance entropy between X and Y. So if I have 2 points inside the space, I do the same thing I read over here. So the limit as epsilon goes to 0 of the limit as n goes to infinity of 1 over n log of this epsilon distance from X to Y. To be a little more precise, I need to restrict to some open set. So let's suppose that these are, yes, Kevin points out that I forgot which metric I'm supposed to be. I want the dynamical metric, which is getting finer and finer. So how many steps does it take to connect things by open sets? Yeah, and a much less obvious thing, but thinking about torus endomorphisms convinces you that for this to be interesting, I really want to restrict to open sets. So X and Y are in some open set, and I want to look at the growth within some open set, which I guess I should assume is path connected. So, and I claim that this encapsulates this expansivity. That if I look at the expansivity of f on x, that this is I didn't take a log when I did that one, so I'll take a log now. That this I claim is equal to the minimal growth of this kind of chain of paths here between 2 points inside some open set over all distinct points inside some open set inside of X. Right, so
quick question, Dylan. I mean, this roll of set is a little bit mysterious here. So why can't you just take the whole space?
Oh, Why can't I take the whole space? Let's look at the map from the torus to itself, which is I take, I want to write it in matrix form, and I take the cat map. This is not expanding, and various things break. Like, I think there should be a version that works for things that aren't expanding, but various things in the definition do break when when it's not expanding. So let's multiply that by 2, so that this is a 4-to-1 map from the torus to itself. This one had eigenvalues, golden ratio, and its inverse, multiplied by 2. Now they're both bigger than 1, and okay, let's continue with this proof. Like why I need this restriction. There's still 2 different directions of expansions, and one of them is going to be much faster than the other. They're both expanding, but one's much faster than the other. And right, and I want to take the minimal one. So like, to connect 2 points, in general, I want to go along the I'm going to want to go along the direction of maximal expansion, and then take a very small detour across the grain in the least direction. And so if I didn't have this restriction to U, I would get well, first of all, I claim, like, you should believe that in this example, like, there's a sort of obvious Euclidean metric expanded by 2 over the golden ratio. And that sort of, from my first metric definition, seems like it should be the maximum amount you can expand. But if I don't restrict to U, then I claim it's always growing like the larger quantity. Right, but then, I just restrict to an open set, and then I can't always go with the grain that's going faster. I should say that I'm sort of maybe 90% certain of this claim. The one that I used before is the one where it's really much easier. If I want to show that this thing about the expansion is less than this thing about the distance entropy, there's just the following easy observation. An epsilon chain for this, if I have something that's expanding at some ratio of lambda, then an epsilon chain for the sort of nth derived metric here is by definition an epsilon over lambda to the n chain for my original metric, if this space is lambda. I'm punning on epsilon, but actually I do kind of need the same epsilon there to make sure that I'm in the domain where the dynamics is actually expanding at that rate. Like, right. I'm staying close for all this long that I must have been very, very close to start with, and exact quantifiably, I have to be that close. And then you translate it through, and you get that answer. And for the other direction, this is the one that's slightly more delicate, and I haven't checked all the details, but this is, again, where I'll just invoke the magic words of that from this pattern of, like, implicitly, I have a pattern of open covers by epsilon balls here and the forward images, and I look at, I construct a graph out of that and look at the visual metric. with the discount factor, that's a little bit worse, so you don't know that it's realized, but you should get the same thing. Right. And a corollary here is that if X is path connected, I mentioned this earlier, the distance entropy is less than or equal to the topological entropy. So here, this one here depends on X and Y in general. And this one here is universal. This one here is just the total volume, everything you need to. So here I'm looking at an epsilon net covering the whole space. Here I just need an epsilon chain. But the worst that a chain could do is cover every single point in my epsilon net. So this is sort of trivially bound on the length of any epsilon chain, if there are any epsilon chains. And this was the proposition that I claimed earlier.
Dylan?
Yeah.
Dylan? So
yes.
Kevin was asking what was U in the theorem. So I guess when you take a minimal in the previous slide,
yeah,
minimal, then you move U and X and Y, not only X and Y.
Yeah.
So you take all possible path connected sets. Is that correct?
Yeah, yeah. I mean, and so yeah, yes. I mean,
okay.
So obviously, you don't want to this is still kind of unsatisfactory in that in principle, it looks like I have to check all X and all Y and all possible path connected sets, which looks like a giant thing I want to check. I think it should be true that it's enough to look at some set of U that are evenly covered, if in the case that it's a covering map. There's a lot of things that I haven't checked there.
Then another question.
Yes.
If you don't multiply by 2 in the previous example, what is your distance entropy?
If I don't multiply by 2, what is the I don't multiply by 2, right? So I look at an actual automorphism. I had an answer. I thought about this because I cared about invertible dynamics as well. Something breaks. I thought, what is breaking? I somehow yeah, well, okay, I'm not getting the answer. I mean, maybe you get 0 or something. I'm not getting the answer. Okay, let me say some moral things about what I would want. This seems to be encapsulating the direction of minimal expansion. If I don't multiply by 2, then the direction of minimal expansion, you're not actually expanding. You might expect that this. You have to go back to the earlier definitions. There's no expansion thing, it's not actually expanding. So, but if you sort of naively follow things, you might expect that this is 1 over tau, which is less than 1. And now I'm not allowed to take the log of it. But also they're just always, because it's shrinking, things are just always going to be connected. Yeah, I mean, like I take, yeah, this distance just doesn't grow in the direction. Right. If I look at dn, I'm looking at the maximum. If they're connected in the shrinking direction, then this distance doesn't actually grow. So the distance of 2 points that are connected by the stable foliation just get contracted, and this distance just equals the original distance, and it doesn't grow at all, and I just get 0.
Thank you.
Which was not a very interesting answer. So that's why I was, multiplying by 2. Great. How I think, so that was the reformulation, and I know I should leave some time, a little bit of time, at least some time for questions. Let me just briefly say, let me just say a few words about this last point on Lipschitz stretching. So you can ask about other rates of Gauss. Like I proposed here that you looked at the minimum over all x and y and all u. What if instead you say you look at the maximum instead of the minimum? And on the one hand, I don't know that you need to do this sort of localization. But on the other hand, well, let me give the more metric version. So we have, again, a dynamical system here on some compact space. And let's define, such a dynamical system, you can make let's suppose the function can be made Lipschitz, which it usually, maybe always can be. But in any case, let's look at the least Lipschitz constant that you can get over all metrics. Infimum over all metrics of the Lipschitz factor of f on x with respect to my metrics d. You think about this a little bit, and you think about the Cox snowflake, where, like, maybe I iterated twice. This one maps to that one. The Lipschitz factor here, this one mapping to that one, is a factor of 3, and you wanted a factor of 4, and I got better than a factor of 4 by snowflaking the metric. So maybe I do something silly like restrict to path metrics to avoid this snowflaking. Which now that's a pretty bad thing to do, because I now need to construct path metrics, which are much harder to construct than more general things. For many cases, I know there are path metrics. There are substitutes, for instance, only requiring approximate midpoints and charging a premium if you do, or looking at instead this reformulated version. And let me just close with a conjecture. So that for f, a polynomial, a hyperbolic polynomial, so previously the answer was not actually very interesting for hyperbolic polynomials. It was much more interesting for rational maps. But I claim that this Lipschitz factor, in many cases equals the core entropy, which I'm out of time, so I will not introduce, but I know some people know. And let me add some asterisks to make this correct. This is only true if the core entropy is positive. But it does seem to be true in those cases. And then this is then interesting because it suggests an extension of the core entropy to all rational maps and not just polynomials, which is where it's been studied previously. Great. Okay, so thank you very much. I see Yemenin is here, so I'm happy to take a few more questions, but I know we need to switch speakers.
Yeah, thanks a lot. Yeah, let's open the discussion. Any comments or questions? Is there any version of this for actually non-locally injective maps, right? I mean, your expansivity definition requires, I guess, local injectivity. Otherwise, it doesn't make sense, right?
Yeah, this is a correct. This is maybe what happens here. What happens here?
I mean, I'm in your
yeah. The question is, I thought only briefly about that. That is like certainly to, if I wanted to remove hyperbolic there, that would say include other types of maps. Yeah, I don't have an answer offhand.
Well, I mean, I'm thinking of expanding Thurston maps where we introduced what we call the combinatorial expansion factor.
Yeah.
And it seems that it's very closely related to your lambda.
I see. Oh, great. So you're saying the combinatorial expansion factor.
There should be some relation to what you defined. There's a very feel.
Yes. Okay. Kevin is here. Unfortunately, I know Kevin cannot speak because he is proctoring an exam and presumably would be able to answer this better. Yeah, I also don't know the answer.
Yeah, let me just throw it out there. I mean, maybe we can all think about this.
Yeah.